I thank you very much, Ken. When I first came into this room, for someone that's going to talk about global warming, it was cold. And I was a little bit concerned that there was some bias being applied by making the room super cold. I'm going to try to take you through, for the next 40 or 50 minutes, some of the science involved in looking at historical as well as future climate change. At the end of my talk, I'm going to say a few words about sea level change because I think that's an issue of great importance in this area. And then finally, I'm going to say a little bit about this movie that just came out day after tomorrow. I'll try to cover some of these points. Is our climate system changing? What is in a climate model? Verification of climate models, and then model projections of future climates, and I'll probably concentrate on the next 100 years or so, and then sort of mitigation versus adaptation. First, I'd like to just give you some brief overview of what sort of establishes on the climate, and I think that this figure essentially shows how on the climate is established. Mars, for example, is an atmosphere, has the very little in the way of sort of greenhouse gases, for example, like carbon dioxide. So its average temperature is minus 50 degrees centigrade. On the other hand, you have Venus, which has an atmosphere that has 95% carbon dioxide, and its average temperature is roughly 420 degrees centigrade, so double that to make it Fahrenheit. So it's very hot there, obviously. On the Earth has 0.04% of carbon dioxide in the atmosphere, and the average temperature is 15 degrees centigrade. So that we already know from just basic planetary science that the more greenhouse gases that you have, the warmer the planet's going to be. Now, in order to understand how this greenhouse effect works, if you look at this simple sort of diagram, you have the sun's energy coming in. Some of it is bounced back out to space by clouds, and some by the Earth's surface, for example, over ice and snow surfaces. So the absorbed amount of solar energy is one part of what determines on the climate. And then on the other the part is the infrared radiation. This is on the radiation you can feel with your hand, for example, when you put it over a hot burner, is infrared. And on that case, if you have more water vapor or more carbon dioxide, you can get a warmer climate. Now, what really determines on the climate is the balance in between the solar absorbed and the outgoing infrared radiation going back to space. So these two factors really determine the temperature of the planet. Here I want to show what ice cores show us. If you go back roughly 400,000 years from the present, you can actually capture in the ice cores over Greenland and over Antarctica, as you drill down into the ice, the actual air that is captured in the ice as air bubbles. And it's captured, in the same sense that when you have an ice cube, you'll see a little bit of air in the ice cube. Well, you can capture the air that existed at these previous times. And you can see that the carbon dioxide has gone up and down for the last 400,000 years. And then on the bottom part here, you can actually measure the temperature by looking at something called the oxygen 18. I won't go into the details of that, but you can get a temperature record for the 400,000 years. And you can see that when the carbon dioxide is high on the temperature of the of the planet was relatively warm, and where it was low, there was low carbon dioxide. So there's a very good correlation between carbon dioxide and temperature. If we look at the last 140 years, from essentially 1860 to the present, you can see that the temperature, let's see, yeah, if you look at the temperature here, it's been increasing from essentially 0.4 up to the 0.3 on this scale, and if you have to multiply this by a factor of 2 because this is in centigrade to make it into Fahrenheit. So roughly the temperature has increased over 1 degree Fahrenheit globally. Now, if you go back even further for 1,000 years, and we can get some estimates of this from looking at tree rings and coral sediments and other proxy data sets, you can see that the period essentially from about 1860 until the present is highly unusual, certainly over the last 1,000 years. And just recently, these records have been extended back for another 1,000 years to 2,000 years, and the warming that we're seeing in the last century is highly unusual, much larger than sort of natural fluctuations. You can ask the question of where did it change mostly? Well, here we have the trends. On the largest dots are 1 degree temperature increase per decade, in other words, every 10 years. And you can see most of the temperature changes have been over the land areas and tending towards higher latitudes. And we think we understand all of that, but essentially, basically, on global warming has been fairly non-uniform, mostly over land and smaller amounts over the ocean areas. We also see shrinking Arctic sea ice. Here's 1979, this is 2003, and you can see it in sort of dramatic fashion here, going from 1979 up until the present. And as you go into the future, and they just extrapolate this out, so that by 2055 or 60, there's very little Arctic ice. The oceans have also warmed up. What I showed earlier was the atmospheric air temperature at the Earth's surface, and here we're essentially looking at the ocean observations from the 1950s up until the present. And I might add that the model calculations are in the shaded area and the observations are in the dashed area. And here we have for the South Atlantic, South Pacific, Indian, North Atlantic, North Pacific, and for the global. So that there is a pattern of global warming, not only for the atmosphere, but also for the upper part of the oceans. And kind of what's important for sea level change, which of course concerns everyone around here, is the warming of the oceans, because that causes a thermal expansion. When you heat up a material such as the oceans, it expands, it warms up. And so you can get an increase of the sea level pressure. Now the glaciers are also melting. Here's Switzerland in 1930, and here's the same scene. And as we go to Alaska, the same sort of picture on the glaciers have melted significantly. Here's a picture in South America in 1976 of a glacier in Peru, and this is that same spot essentially 20 years later. So you can see that the glaciers around the world are melting. Now these are the small glaciers, the ones over the continents, over Europe and US. So they don't change the sea level very much. They contribute some to it. But the big glaciers, of course, are over Greenland and Antarctica. And there we're finding from satellite measurements that the blue areas are where the glaciers are melting around the tip of Greenland. And actually, it's accumulating more snow on top of Greenland, because when it does snow now, it adds more snow at the top. I think the real danger for the longer term is that Antarctica and Greenland will substantially melt. If those do melt, then we're going to see sea level rise significantly, because they have huge amounts of liquid water that would essentially get dumped into the ocean and then raise on the sea level. But the first order effects that we see right now are basically from thermal expansion, in other words, the warming of the oceans. Here I just want to give one example. This was taken just a year ago at the base of Greenland. We're getting these big rivers starting to form as the glacier melts around the lower elements of the Greenland area. Another feature of global warming and climate change is the percentage of rainfall amounts that exceeds essentially 2 inches over a single day. And you can see that this graph goes from 1900 up to the present, and that we're getting more heavy rainfall. And the way that this happens is you warm up the atmosphere. It actually, in an exponential way, can hold more moisture. And so when it does rain, the rainfall is more intense and heavy. And you can see from this graph the enormous amounts of flood damage in billions of dollars. For example, in some of these years, it got up to $16 billion worth of damage. Now I'll try to explain what's in a climate model. I've been a climate modeler since 1963, so 40 years. And I've run on the world's fastest computers ever since. I'm actually using a computer now in Japan called the Earth Simulator. It's a computer that costs $360 million. It's the size of a football field. The electricity for the computer costs $12 million a year. And now for the cynics in the audience, this computer generates lots of heat. So as we carry out studies of global warming, we're causing global warming. Here I show in a very schematic fashion what we include in our climate models. Obviously, the energy coming in from the sun, in other words, the solar flux. We also include the outgoing infrared energy going back to space. In other words, going back to what I said a little bit earlier, you have to have the balance of these two things. We include clouds. We have cirrus clouds, in other words, the very high clouds. We have cumulus clouds, like the clouds you see around here quite a bit. We also have layer clouds. And the cloud interactions are still an area of large uncertainty about how we include those, because you can imagine trying to understand and simulate the complexity of cloud systems. That we also have in our model mountains. We have snow cover prediction. We have soil moisture. We have vegetation. We have rivers that sort of run the soil moisture out to the oceans. We have ocean models that capture, and I'll show you some examples in a few minutes, the ocean eddies, the Gulf Stream, and all of those sorts of things. We have sea ice. And we have transfers of the radiation, the evaporation, and the precipitation. In other words, and we essentially mimic virtually every one of the interactions that are in the climate system. And our computer models are of the order of 500,000 to 1 million words of code. So they're huge efforts. They involve hundreds of scientists and programmers putting together code that can run on modern supercomputer systems. I mean, typically, when we ran these models in the 1960s and 70s, we had resolutions that were somewhat similar to what you can see here, kind of blocky continents and ocean bottoms. And then as we go to higher resolution with faster computers, we can essentially mimic on the shape of the mountains and the ocean bottom and things of that sort, so that we've improved that significantly. Here I just want to show a simulation. Now this isn't clouds, it's actually the water vapor. So there's more water vapor in the tropics than there is in the higher latitudes. And what you're looking at here is storm systems in the mid-latitudes in both the southern and the northern hemisphere. You can see some circulation systems. And the precipitation is actually on these orange areas. So that these simulations of the atmosphere are quite realistic compared to what we were able to do maybe even 20 years ago or 30 years ago. And part of that's just that we have faster computers, but we're also learning how to deal with things like the radiation and the clouds and the precipitation mechanisms much better as time goes on. Here I just want to show an ocean simulation. There's a lot of activity of the oceans right along the equator. You've got big eddies forming. You can see those eddies. You can get the Gulf Stream moving up into the higher latitudes, so that we're able to capture El Niños and other very important phenomena between the atmosphere and the ocean with these ocean models. And I'm going to show you another figure, essentially showing, in just a second it'll be coming up, that in the ocean, the eddies and the currents are much more narrow than in the atmosphere. So that means we have to use a higher resolution model. And you'll be seeing here on the Gulf Stream, for example, going over here, you'll see eddies virtually everywhere over the world's ocean. And this has been one of the things that we have been trying to figure out how to deal with, but we can't find any shortcuts. In order to solve these equations by brute force computer techniques, we require these very fast and very large computer systems in order to carry out a simulation. Also, sea ice is another important quantity. Here's on the sea ice thickness. A lot of sea ice comes down on the coast of Greenland. This is Greenland right here. On the ice fractures and breaks, as you would expect, because it's sometimes a kind of a plastic viscous fluid. And you get piling up of the ice on the north side of Greenland and here in Canada. So we're able to do a reasonably good job now of sea ice. In the early days, we sort of ignored all of the complexities and overly simplified our models because of the lack of computers capability. But now we can do a pretty good job. Now here I want to show something about how we can dissect what goes on in the climate change. Here we're going from 1990 up to the year 2000, or actually 1870. And so in order to kind of answer the question, what's causing what in terms of the climate change, on the black line is the observations. And the observations are shown here. And they essentially show that from 1870 up until the present, the climate system has warmed up over 1 degree Fahrenheit. Well, we can include in our model sort of the natural forcings on the climate system. And those natural forcings are volcanoes and the change of the solar variations in the forcing of the climate system. And that's the blue line. Now, instead of just carrying out one experiment, we carry out a statistical sample of an ensemble of 5 members. And what you see in the blue, on the shaded blue, is the range of the 5 members of the ensemble, and the mean is the dark blue line. So that for the first part of the century, that the volcanic and solar explain a lot of the warming. However, if you just include those effects out to the year 2000, you get a much cooler climate than the observed, which is in the black. Now, if you include anthropogenic changes, and those are the increasing greenhouse gases, most of it's CO2, and the sulfate aerosols. The sulfate aerosols are the things that when you are flying over cities and you see kind of a haze, a lot of that is from the sulfur dioxide that gets put into the atmosphere, which forms little particles, sulfate aerosol particles, and those tend to act to cool the system. So if you include the greenhouse gases and the sulfate aerosols, and you can see that we do a pretty good job of reproducing in red on the observed. In fact, on the volcanic events, for example, the Mount Pinachudo eruption and El Shishan, we show a temporary cooling of the climate system, and then it quickly recovers. So on the main point of this figure is to show that in order to reproduce the observed figure or the pattern, we have to include the greenhouse gases. And so there was a panel, international panel for climate change, made up of hundreds and hundreds of scientists who looked at all these figures, not only from our group, but other modeling groups around the world. And they came up with the conclusion that mankind is increasing the global warming by introducing greenhouse gases above their normal levels. So that was a rather profound statement. Now, not everyone believes that. There are still skeptics, and I think it's healthy to have a skeptical view, but certainly on the observational evidence is very strong. This is the kind of evidence that's very similar to the evidence that smoking causes cancer. You have to put it together piece by piece to sort of understand on that sort of analogy. Now I'll talk a little bit about the future. Here's a article or a picture from Time magazine, which I think is pretty accurate. It shows on the countries that emit greenhouse gases, especially on the carbon dioxide, and you can see that the U.S. is a major source. Here's Canada, Europe, over here, Japan, and China. Now, probably on this is 2001. My estimation is that China and Southeast Asia probably have increased substantially, even in this last 3 or 4 years. So that we haven't done anything to sort of curb on the increased carbon dioxide into the atmosphere. Here, let me skip this. If you look at the end of this century, 2090s, we expect that from our modeling studies that the major changes will be in the higher latitudes. Here's 4 degrees centigrade, so you have to double that to 8 degrees Fahrenheit. And we're already seeing that, of course, over Alaska. If you go to sort of Alaska and Siberia, you're seeing enormous changes in the climate system. On the smaller changes are taking place over the oceans, and we think we understand that in the sense that the oceans have an enormous heat capacity, and in order for the oceans to warm up, it just takes time. But eventually they will also warm up. But even in the tropical oceans, they're up to the sort of 3 or 4 degrees of Fahrenheit temperature, which is an enormous increase. Just keep in mind that anytime you're over say 85 or 90 degrees Fahrenheit in the tropical oceans, the intensity of hurricanes increases significantly. I hope that that's not terribly bad news for all of you around here. But I think the reality is that we know there's a very good correlation in between intensity of hurricanes and the ocean temperature. Here's a kind of a composite figure, essentially going back for 1,000 years, and here's carbon dioxide increasing, here's methane increasing, here's sulfate aerosols increasing, and then actually gone down a little bit, mostly from the fact that we've had to clean up the air a little bit. And then here's on the temperature, and here on the end of the graph actually ends at the year 2000. But if you carry it out from the model calculations, and the models give different answers, out to the year 2100, you can see that the temperature, the globally average temperature, will increase by the end of this century by either 2 degrees or up to 4 degrees centigrade, double that to turn into Fahrenheit. So this is an enormous increase in the temperature. Obviously, several things will be affected by climate change: health, agriculture, forest, water sources, coastal areas, and I'll come back to the coastal area issue, and the species and the natural areas. On trees, for example, have a very long time scale as they change from, say, deciduous trees to evergreen, and even though the climate may have changed, it takes a while for the ecology to sort of adjust to the new situation. Well, let's see what should we believe. On the atmospheres and the oceans are warming, consistent with the model calculations. Glaciers are melting. We have lots of evidence of that. The temperature, the rain, and the snow and observational trends are consistent with model simulations. In other words, there's going to be less glaciers, less snowfall, but the rainfall and the temperature are going to increase. And the simulations of this last century are pretty consistent in between the model and the observations. And the global changes are much larger than can be explained from natural variability of the climate system. And I referred earlier to the International Panel of Climate Change, which involved hundreds of scientists. And here's on the official statement that they made. An increasing body of observations gives a collective picture of a warming world and other changes in the climate system. And here I sort of already have covered a lot of these issues. I won't go into that. There's more and stronger evidence that most of the warming observed over the last 50 years is attributable to human activities, mostly due to increasing carbon dioxide. There's also been drastic changes in the world's population and ecosystems. Human influences will continue to change atmospheric composition throughout the 21st century, irregardless of whatever we do. So now I think that statement needs a little bit of careful consideration. In other words, if we don't do anything at all, it's obviously going to get higher concentrations of carbon dioxide and other greenhouse gases. If we do something like the Kyoto Protocol that you've seen about in the newspaper, and the president of Russia, Putin, is considering signing it. If he does sign it, then it'll become international law. But even if he signs it and we start to do something about global increasing greenhouse gases, it will still take a long time for the climate system to change. And it's not going to stabilize for a long, long time. Unless, for example, we suddenly switch to the use of nuclear energy sources or things of that sort. So I think on the issue for us is not whether we're going to benefit from it, but whether our grandchildren and great-grandchildren are going to benefit from the actions that we take now. Now, I've talked mostly about the changes of the means, but we can expect changes in the extremes. For example, heat waves. We've already done studies on the number of heat waves that will probably take place over the next 50 or 60 years. And cold snaps, speaking about, and floods and droughts. On the freeze dates will change. For example, in England, the growing season is a month longer. In parts of the U.S., we have growing season that has been extended by several weeks, which is good. So remember, for some things, global warming is good. If you lived in Canada, you would like to have a warmer year. If you're living in Florida, I'm not sure you want it to be a lot warmer than it already is in the summertime. So, there's some good things and bad things from global warming. On the precipitation intensity, I've already mentioned it's going to increase. On the diurnal temperature change, in other words, on the day-night temperature change, we can expect that on the nights will be less cold because you have more greenhouse gases and more water vapor in the atmosphere, and therefore it doesn't get as cold at night. We can expect disease and health patterns will change. For example, even many of the diseases that you've heard about, West Nile and other ones, are temperature-dependent diseases. So as the system warms up, we're going to have more tropical types of diseases moving into mid-latitudes. And of course, ecosystem changes. Forest, food supply, biodiversity, land use, and the pollution are all factors which we'll have to face in the future. Now, I show this is that we're basically living in a world environment where we have to work with other nations, and we have to try to work out how we're going to deal with climate change as a worldwide problem. And it can't be dealt with just as a problem for the individual country. And I think climate models can help on the policymakers determine various options. Obviously, sort of mitigation versus adaptation. I think likely both options have to be explored. And here again, climate models can help us sort of sort these things out. And this may be a kind of on that word at the bottom, geoengineering is needed. It's clear that mankind is changing on the planet. And I think that we need to start thinking about how do we want it to sort of be in the future. Who are going to be the winners and the losers? And I think some of our computer modeling studies will allow us to search out those options. And it'll be very difficult, I'm sure, for the various political bodies to figure out which way we should go, because most of our political bodies are reactive bodies. When something bad happens, the political engine turns on and comes up with sort of solutions. We're less good about how to do something before a disaster happens, or if we have a sort of a disaster in the making that's very slow. Then finally, I think I'll end up here. How is sea level changing and why? And here I want to point out in this graph of sea level change from 1993 up to 2001. And I'm not speaking at this point specifically about Florida, but just in a global sense. Here we're seeing since 1993 up until on the present, the satellite observations of sea level pressure on sea level change are shown in the dotted lines, and then the smooth line is the yearly average, so you can see it's been increasing. And the dashed line, which is shown here, is due to thermal expansion. In other words, as the oceans have warmed up a little bit in this short period from 1993 until the present, that just from that warming up of the oceans, you get the expansion of the sea level. And so that we now have with satellite capability the observations of sea level. So it's not dependent on people going out and measuring it at various places around the world, because it's always a difficult problem, is how you measure sea level. In some parts of the world, the sea level is rebounding from the last ice age. And for example, if you're in the Northeast, along the coast, off of the coast of New York or Maine, on that land is actually bouncing back up from the fact that the ice on the huge glaciers have melted. So it's a little hard to kind of measure it in various parts of the world. And I won't go into the details of all of that. But this is a kind of a global sort of measurement. So for the first time from 1993 up until the present, we can actually measure it from satellites, which is going to be great. On the thermal expansion is the largest factor on the short term. However, if the glaciers of Greenland and Antarctica melt in substantial manners, that'll be even a much larger effect than just the thermal expansion. We expect that sea levels will continue to rise up to 0.5 to 2 meters. And this 550 is the concentration of carbon dioxide. So this would be towards the end of this century. So you can expect maybe 6 feet at the worst, and here about 1.5 feet. So on this is an estimate based upon several factors. If we don't do anything about the greenhouse emissions being stabilized, then we could expect that the sea level rise would be 4 meters, or if you multiply that by 3, 12 feet. And this would have sort of applied to the early part of the next century. So that would be after 2100. And I think that roughly, I have a hope that things will be dealt with in terms of greenhouse gases by then, and we won't be into this essentially 4 times the present amount of carbon dioxide. If we are, we're in deep trouble.
That's without the ice cap melting, right?
Huh?
Is that without the ice caps melting?
Yeah, I think that assumes that the ice caps haven't melted,
Yeah.
but they will have melted, I think, by or a large part. Now here I show the past and the future sea ice, or the sea level. If you go back to the last ice age, where there was lots of ice that was domed over the northern U.S. and Canada, a huge ice sheet. Well, if you put that much ice onto, or I should say, on that much water into an ice sheet, then obviously that lowers on the sea level. And what you see here in the green is that Florida was much more land covered than it is. and that the sea level is actually much less. Now, if you take on the worst possible scenario and you go out for sort of 200 years into the future, you can see that Florida is going to be much smaller, and that New Orleans isn't going to be connected anymore to the land or the continental area, and therefore on the coastlines are going to be more inland than they presently are. I'm hoping that there'll be some sorting out of this process in the future, and I think a lot of the political action will have to take place with where this lands. Now, I've been asked by a lot of radio people and television people. CBS talked to me yesterday about my thoughts on the Day After Tomorrow movie. I think you've seen clips of it on your television screen, and I can tell you that the facts are not quite right in that movie. But as you know, the people who make movies like to exaggerate a point, and it is interesting but not realistic. And I'll come back to that in a minute. They show global warming taking place over a few days, whereas in reality it'll take place over decades to century time scale. There will not be abrupt climate changes in the sense that they talk about them over days, but we've had abrupt climate change in the past. I can tell you two examples. At the end of the last ice age, there was a huge lake over the Gulf of St. Lawrence. And one day that lake broke free and sent huge rafts of icebergs all the way over to Spain in just a few days. And the way that we know that is that when we look at the ocean sediments off the coast of Spain, we can see that the rocks at the base of the icebergs had actually come from Canada. And so that we know that there was huge melting that took place, and there was this huge lake that suddenly broke free and flooded the North Atlantic. And in fact, what happened, which has some fictional aspect to this movie, is that the North Atlantic suddenly became fresh from all of this fresh water from the melting of the ice sheet over the North Atlantic, and the Gulf Stream suddenly stopped for a few decades. And what happened then is that it sent Europe back into a minor ice age that lasted several hundred years, and then it popped back out of that. And the reason was the Gulf Stream wasn't transporting all of this warm water and heat up to the higher latitudes. It had, on the Gulf Stream, had taken a right turn, and instead of going up to Iceland, it actually headed over towards Spain. So that we know that those sort of things can happen, but they have time scales obviously longer than a single day or so, as you'll see in the movie. in the last part of the movie, it shows the Statue of Liberty ice covered. I don't think that would be the result of global warming. I think global warming will be probably taking place, but it won't suddenly switch us back into an ice age. Remember, the ice ages, the in and out of ice ages is primarily caused by the orbit of the Earth around the sun and the small shifts of the orbit. And we have lots of paleoclimate data which verifies on the role of the orbital changes of the Earth going around the sun, is explaining basically going in and out of ice ages. So we're seeing now for the first time that man is actually having a large influence on the climate system. I want to thank you very much, and I'll be happy to entertain questions.
Thank you very much. I have two quick questions. One, you didn't mention salinity and whether these, whether there's much influence associated with the rising or falling salinity. And the other quickly is, you mentioned the surface levels of the oceans and temperatures. Have there been any studies with any of the deeper areas in temperatures? Okay, well, I can maybe try and answer that question. Now, obviously, we don't have a lot of what I would call observational data going back, right. But we do have kind of model calculations, which we first verified to sort of explain on the present climate. Kind of what we see, for example, is that when you warm up the climate in the wintertime, especially, you get more precipitation in the higher latitudes. And what that does over the oceans is it makes the ocean waters fresher. In other words, the salinity goes down. So that instead of having as we do right now, on the cold, highly saline water, high salinity water, actually sinking all the way down to the bottom of the North Atlantic Ocean and then flowing back towards the equator, that as you lessen on the salinity by having more fresh water, the water does not sink as far, and the circulation system from the Gulf Stream to, say, Iceland, and then sinking and then going back towards the equator happens at a shallower level, so that the bottom of the ocean becomes more isolated because that's cold and highly saline water. And so we're seeing some indications of that, but our problem is that we don't have very good sort of measurements in the deep part of the ocean. But there's lots of oceanographic studies now that are taking place to try to quantify that. But as far as I know, the models are simulating the first order effects fairly accurately. Who picks out? Oh, okay.
I find your evidence really compelling, and I think I'm frustrated because of the report that I saw from the Bush administration that seems to discount the fact that humans are the ones that are really responsible for what he calls climate change, but I would rather call global warming. I think even the use of the word climate change is misleading. How do you, I don't mean to turn this into a political debate, but how do you account for what I see as almost a blatant disregard to the scientific community's findings?
Well, yeah, obviously, in my position as chairman of the National Science Board, I try to be as apolitical as possible. However, in my other hat, I am a scientist who tries to understand and sort out the scientific facts. And
I can't explain exactly why there's sort of ignoring of this problem. And I won't. And I think that you can read the newspapers and the columnists sort of columns as well as I can. But I can just tell you from my own experience of dealing with the White House. I've gone on record. I've testified to Congress. I've done all the things that a scientist can sort of do to help inform on the policymakers that this is a serious problem. And there's many of my other colleagues out there that have just as been as strong in asserting on their concerns. As a public citizen, I think that we have enough scientific certainty at this point to start taking serious steps, and I think it's the responsible thing to do. Sort of putting off a long-term problem makes it harder to sort of deal with later on. So I think this is the time that we should start addressing it and figuring out ways to improve energy conservation, improve our method for finding other ways to generate energy. I don't think anybody wants to cut back on lifestyle changes, but on the other hand, we have a responsibility to deal with this. And if you go, and many of you probably been to Europe. For example, everyone has cars in Europe also, but they use cars mostly for pleasure driving on the weekends and that sort of thing. And they've built sort of mass transit systems that are very efficient. In other words, I favor, just speaking personally, a modest increase of the gasoline tax to help subsidize on these more energy efficient ways to deal with on carbon dioxide. And I think that that's the sort of thing that we need to do. When we talk about a market-driven economy, the environment doesn't kind of get very much weight because it's not a marketable thing in the normal sense. So I'll let someone else ask a question. Thank you for raising that.
Two questions. I noticed that in the graph, it seems like right around World War II, there was a spike in the temperature. And also, is there any type of distributed computing applications in the works that would help modeling the atmospheric projections and just maybe even day-to-day weather?
On that spike is where, did you say?
It looked like right around 1939 to 1950, there was a temperature spike, and then it dropped off, and then it went right back up. And I was wondering if World War II would have had anything to do with that.
Yeah, there's on the cooling spikes are essentially caused by the volcanic eruptions. Kind of what we don't have good observations on is the solar changes. We've only got recent observations of the solar changes, but we think that the 1930s in part can be explained by variations in solar intensity, but that's still kind of a guess because we don't have very accurate measurements of on that quantity. And then finally, your question about computing capability it turns out the nature of the equations that we solve for the atmosphere and the oceans and the sea ice require a computer that has a fast network. Because we have fast enough processors, but we have to solve the equations by using numerical techniques that require sort of rapid communications with all the processors all at once. And so distributed computers are harder for us to use on this kind of problem. It's a mathematical limitation of the type of equations we have to solve.
Since the alarm was first raised about global warming, has there been any change in the rate of change? Has it had any effect whatsoever that the scientific world has pointed out what's happening?
I think at this point, the change has been rather uniform since the 1970s when we first started pointing out that global warming is a really seriously issue. On the way that it sort of works is that as the carbon dioxide goes up, the atmosphere warms up a little bit, but then the water vapor that's in the atmosphere can increase exponentially, and so that we are on a very rapid rise. And unfortunately, unless we start cutting things back, it's going to take probably a century time scale to sort of bring it back. Often you've heard about the Kyoto Protocol, which is to cut the emissions back to the 1990s. Even if we did that, and that's going to be extraordinarily difficult for us to do that, the climate system's going to warm up a great deal, even if we sort of brought the emissions down to on the 1990 levels. It'd probably have to take 50 years for it to kind of warm up and then start to cool off and then come to a new equilibrium. If we don't do it, then it'll equilibrium at a much higher level than we have anticipated.
In terms of response or lack of response, there's a tendency to point to all sorts of sort of negative things like politics and people's unwillingness to change lifestyle, et cetera. But on the other hand, a lot of these things are really sort of hard to understand or for people to understand. Just the non-linearities. We're sort of linear thinkers. We expect small causes to have small effects and not big cascades. The interconnectedness of things. A lot of these things are just sort of unnatural for us. So the other side is we really don't understand in some sense.
Yeah.
My question is, how well do you think this stuff is getting into the educational systems, including the ability to simulate that we've never been able to do before? The other side is sort of the positive. We need to make a smarter population. Mm-hmm. And what I'm just asking about, what do you see your appraisal of how that side of things is going? Yeah,
on the educational side, I think that's where we have to deal with scientific facts as much as possible, because just like when I spoke to all of you this evening, I didn't want to give you my prescription of what should happen in detail. I think that I wanted to first deal with the scientific facts. Okay. Now, when you get to the place of where sort of what society ought to do, I think there has to be a great deal of debate about that. The science isn't going to sort out all of the impacts. And I think that, at least my view is, okay, we don't know the complete answer yet, just like with the smoking and cancer situation. We had early indications that that wasn't good for you. And I think that if you take steps at an early stage versus a late stage, it's much easier to sort of deal with. And I think that the education that we see sort of taking place. I've been on Nova. I've been on public television with Meryl Streep and other things like that. And I think that responsible scientists try to do exactly what I'm doing this evening, educate. And then every summer I speak with hundreds of high school science teachers and try to explain where the science is as a way to hopefully educate on the present and future generations of citizens. So I think we all have a responsibility.
Thank you, Warren.